AP Physics 1, Workbook, Unit 4, Work and Energy, Activity M, Energy and Projectile Motion. Please remember to pause or rewind the video as necessary. Read the scenario along with me. A designer is creating an obstacle for an obstacle course where a person starts from a movable platform of height h from the ground. The person grabs a rope of length L and swings downward. At the instant the rope is vertical, the person lets go of the rope and attempts to reach the far side of a water-filled moat. The left side of the moat is directly below the position where the person will let go of the rope. The designer runs several tests in which the rope has different lengths and moves the platform such that the rope is always initially horizontal. The designer notices that the person cannot land on the other side if the length L is very short. The designer also notices that the person cannot land on the other side if the length L is very close to H. In other words, the length of the rope is very long. So a very short rope doesn't work. Very long rope doesn't work. Assume the size of the person is much smaller than both the lengths of the rope or the height in which you're falling from. Let D represent the horizontal distance from below the release point where the person lands. Answer the following qualitatively, citing physics principles, but without manipulating equations. Why does the person land in the moat if the rope's length is very short? Okay, let's map it out with equations so that we can wrap our brain around the concepts involved, and then we'll talk about it. Well, this obviously has change in height, change in speed right here. So this has conservation of energy written all over it. The beginning part would be here, energy initial. Well, kinetic energy would be 0, and gravitational potential energy would be mgh. Spring potential energy would be 0 because, of course, there's no spring in the problem. So the initial energy is just the mgh. Right here, when you release it, would be the final part of the energy problem, in which case you end up with kinetic energy. So we'll write 1/2 mv squared for that. We end up with no potential energy because we're going to treat that as the lowest point of the energy problem. Even though the rest of the problem you fall lower than that, the rest of the problem is a projectile motion problem. Or at least you can treat this as two separate scenarios. Conservation of energy to that point, projectile motion from that point. That will allow you to at least use this as potential energy equals 0. And yes, spring potential energy is also still 0 because, again, it's no spring. So the initial energy is mgh. The final energy is 1/2 mv squared. And that final speed, guys, that final speed right there, that corresponds to the launch speed right here, which would be v naught x, the launch speed of the projectile. Now, you might recall projectile motion kind of depends on two things. In the x direction, the horizontal direction, we have x equals v naught x times t, where x is going to be, I'm just going to write x as d, because x is going to represent that horizontal distance that you fly through the air. V naught x is the launch speed, but that's also the same as the final speed or the final kinetic energy at the bottom of the swing. And then finally, t is the time it takes to fall. Well, in the y direction, you might remember that y is equal to 1/2, or I should say y is the same thing as the height that you're falling from here. So height is equal to 1/2 g t squared. So solving for t is equal to the square root of 2h over g, which means a couple things. One, the distance depends on initial velocity and time, okay? And that's what we're going to wrap our brains around in our explanation, okay? Here we go. Why does the person land if the rope's length is very short? If the rope is short, then the gravitational potential energy of the person-Earth system that is converted to the person's kinetic energy is very small. This results in a small horizontal velocity, so v naught x will be very small. when they let go of the rope. Even though the person will spend a longer time in the air after they release the rope, okay, so what we have here is we have a trade-off. If you start from if the rope's length is very short, that means you're going to drop from a very small height. In other words, you're not going to be converting as much potential energy. Less potential energy will be less kinetic energy, which will be less speed. Less speed, yes, there's more time in the air, but you have much less speed than you do greater time, which means you'll overall have a lower distance, which means, oops, you fall in the water. Why does the person land in the moat if the rope's length is nearly the same as the height of the platform? Okay, let's take a look. If the rope's length is the height of the platform, then what's going to happen is it's going to be a super long rope like this, really, really long rope. And when the person lets go, yeah, they're going to convert a lot of potential energy into a lot of kinetic energy. Okay, which means you're going to have a built-up speed. Your speed, a lot of potential energy because you're falling from a big height, and it's going to be a lot of kinetic energy, which means it's a lot of speed at the top right here, but you're not going to be falling for very long. Doink, you're going to fall. You're going to have much less time than you do speed, much less time than you do speed, so your distance is also very small. So if the rope is very long, the person-Earth system will have a lot of gravitational potential energy to convert into kinetic energy. So the person will have a large horizontal velocity when they let go of the rope. By the time the person lets go of the rope, they are practically on the ground. So using free-fall kinematics equations, the time for the person to hit the ground is extremely small. Even with a large horizontal velocity, the time is too small for the person to travel a large enough distance. So again, they land in the water. Using the following variables given above and fundamental constants, write mathematical equations for the following. V, the horizontal speed when they let go of the rope. Well, for this one, we're going to be using conservation of energy. And again, let's map out what our equation looks like. You're starting with potential energy, and it's converting into kinetic energy. So that's where we're going to begin. mgh equals 1/2 mv squared. And to solve for v, it's going to take 3 steps. Multiply by 2, divide by mass, and square root. So v is equal to the square root of 2gh, but h is really, if you look at the problem carefully, h is going to be the length of the rope. It's not this h. You need to be careful. That's the h from the platform all the way to the ground. It's not the same h. H that you drop from, the height that you drop from, if you're dropping from a horizontal here, is L. So to see it more clearly, here's where you're starting from. That's the length of the rope. And here's where you end up down here. That means the height that you drop from is the length of the rope. So we're going to make that substitution. Instead of 2gh, v is equal to the square root of 2gl. Okay, the distance d. Well, the equation we're using is y equals y naught plus v naught yt minus 1/2 gt squared. Okay. And this is going to be 0. Okay, and what we're going to do is we're going to I'm going to subtract this around. I'm going to subtract this to the other side, and we basically have delta y equals negative 1/2 gt squared. But what's happening here, you're starting at that spot right there. Okay, we're starting at that spot, which would be the entire h, this entire distance h right here, minus L, the length right there. So that would be the remaining height that's left over. So h minus L is going to be that delta y. And since you're falling, it's going to be negative. So we have a negative h minus L equals a negative 1/2 gt squared. The negatives cancel, right? And we have h minus L equals 1/2 gt squared. So let's solve this for time. The reason we're going to solve for time is because distance is equal to v naught x times t. Well, v naught x is the same as your v right here. So we're going to be plugging that in for v naught x. However, we need to substitute for time also. So time, let's move this over here. What do we have to do to solve for time? Multiply by 2, divide by g, square root. So time is the square root of 2 times the quantity h minus L over g. And we're going to substitute that right there for t. And the distance is going to be the square root of 2gl times the square root of 2 times the quantity h minus L over g. Okay, now, since you have two different square roots here, you can put everything under the exact same radical, and you have 2gl times 2 h minus L, I'm just multiplying this times this, all over 1 times g, which would just be g. And if you look and see, you see the g's end up canceling, and this is equal to 4, which the square root of is 2. So this is equal to 2 times the square root of L times the quantity h minus L. Describe how your equations from part B1 and B2 support your reasoning in part A. If L approaches 0, let's take a look. If L approaches 0, then the distance approaches 0. In the first term, 2gl will approach 0, meaning the whole distance traveled by the person is very small. Part C2, describe how your equations in part B1 and B2 support your answer, your reasoning, and your answer of part A2. If L is the same value as each, then subtraction term in part B goes to 0, meaning the distance the person travels is also very small. So as L gets closer to h minus h basically goes to 0, and the whole distance essentially gets closer and closer to 0, which would mean you land in the water.